So what we've shown so far is that 3-SAT can be solved by a non-deterministic Turing machine in polynomial time, and longest path can also be solved by a non-deterministic Turing machine in polynomial time. What we don't know, though, is whether or not those problems can be solved by a deterministic machine in polynomial time. We also showed, using our polynomial time reductions, that if longest path could be solved in polynomial time, then 3-SAT could as well. We were able to reduce 3-SAT to longest path, so that means that if we suddenly had a polynomial time algorithm for solving longest path, then through that reduction, we also had a polynomial time algorithm for solving 3-SAT. That same reduction also allowed for us to conclude that if there was no polynomial time solution for 3-SAT, then there couldn't have been a polynomial time solution for longest path either. Because if we said there was no polynomial time solver for 3-SAT, but there was one for longest path, then we have a contradiction, is the idea there. So now the interesting thing about this is that by answering this question of can longest path be solvable in polynomial time, we can get some insights into what the answer should be for 3-SAT. If we were able to do that reduction in the opposite direction, where instead of reducing 3-SAT to longest path, we reduce longest path to 3-SAT, then we sort of have this together they stand, together they fall relationship between these two problems, where if either one of them could be solved in polynomial time, then so could the other. And if we could show that either one of them was impossible to solve in polynomial time, then we could conclude that the other one couldn't either. So the whole idea for how it is that we're going to be approaching this P equals NP question is by coming up with a large collection of problems that are all in this together they stand, together they fall relationship. In this category of problems that are all going to have this together they stand, together they fall relationship are what we call the NP-complete problems. So the NP-complete problems are going to be this category of problems where if we could show any one of them could be solved in polynomial time, then all of them can be, and P equals NP. And if we could show that that any one of them couldn't be solved in polynomial time, then we can actually conclude that P does not equal NP. And we're going to talk about the definition of this NP-complete category of problems so that we can see why they're going to have this property. So before we can talk about NP-complete, we want to talk about this other category of problems that we're going to call NP-hard. So the NP-hard problems are going to be all of the problems that are at least as hard as any of the problems that belong to NP. So intuitively, these are the problems that are as hard or harder than any NP problem. So they're as hard to compute or strictly harder to compute than any NP problem. And these are going to be the problems that have this property where if we could find a way to solve any NP hard problem in polynomial time, then all the NP problems are going to be solvable in polynomial time. By basically saying if something that was at least as hard as NP could be solved in polynomial time, then everything in NP was going to be solvable in polynomial time. Now, the way that we're going to define this class NP-hard so that it has this property is by using these polynomial time reductions. So the class NP-hard is going to be the set of all the problems such that for every problem that belongs to the class NP, that problem can be reduced to this NP-hard problem. So B belongs to this class NP-hard. So some problem B, we're going to say belongs to this class NP-hard. If for every problem that belongs to NP, for every problem A that belongs to NP, A is polynomial time reducible to B. So that is, we can set up a reduction from any NP problem to this problem B, which says that if B could be solved in polynomial time, that was the only missing piece that allowed us to compute any NP problem in polynomial time. So the idea here is that we could take any NP problem and set up a polynomial time reduction from that problem to this problem B. So that now the only thing missing in being able to find a polynomial time solution to any NP problem you choose is to fill in some polynomial time solver for B, that NP hard problem. So if we could say any NP problem reduces to B, then that means B is NP hard. And if I could find a polynomial time solver for B, then that must have meant that P is equal to NP, because now every NP problem can have this polynomial time reduction to B, which can be solved in polynomial time. Therefore, every NP problem can be solved in polynomial time. So the hardest part about this whole structure of NP hardness, so to show a problem as NP hard is to show that it has this really incredible property that answering the question of can we solve this problem in polynomial time gives you the answer to this question of can we solve any NP problem in polynomial time. So that's a really powerful tool to have, but this is a hard thing to show because we need to show that all NP problems reduce to B in order for B to be NP hard. Now there is a shortcut we can use, again, using these polynomial time reductions. So if we assume that we already had an NP hard problem, so let's assume that we already had some problem that was NP hard, then it's going to be much easier for us to show additional problems to be NP hard. So if I had, let's say, this problem A that I knew already was NP hard, that meant that any NP problem, polynomial time reduced to A. So that now, if I had some new problem B, and I wanted to show that B was NP hard, it's sufficient for me to just reduce A to B in polynomial time. Because if I can reduce problem A to problem B in polynomial time, then since every NP problem reduced in polynomial time to A, and A was polynomial time reducible to B, then and because we can chain together polynomial time reductions to build new polynomial time reductions, we have this sort of transitive polynomial time reduction from any NP problem to B. So that now if I could solve B in polynomial time, then that means I could solve A in polynomial time, which means I could solve any NP problem in polynomial time, and therefore P equals NP. So once we had a first NP hard problem, new NP hard problems are easier to find. We're going to show in an optional video that that 3-sat is actually an NP hard problem. So we're going to just, for the sake of everything else this semester, just take for granted that 3-sat is an NP hard problem. There's going to be an optional video posted where we give the sketch of a proof for how we know that to be the case. But 3-sat is sort of our first NP hard problem. So by reducing 3-sat to any other problem, we're going to be able to conclude that that other problem is also NP hard. So in particular, we showed how to reduce 3-sat to this longest path problem. So since 3-sat, we're just going to take for granted as NP hard, and we could reduce 3-sat to longest path. Longest path is also going to be an NP hard problem as well. So if I could solve 3-sat in polynomial time, then P equals NP, because any NP problem could be solved in polynomial time. And if longest path could be solved in polynomial time, then we could solve 3-sat in polynomial time. So therefore, we can solve any NP problem in polynomial time, and P is equal to NP. So with these NP hard problems, we have a way of showing that P does equal NP. By showing that any NP hard problem can be solved in polynomial time, then we can show that P does indeed equal NP. So any polynomial time solution for 3-sat or any polynomial time solution for longest path would allow us to conclude P does equal NP because they were both NP hard problems. That, however, does not directly give us a way of showing that P doesn't equal NP. So to do that, so to show that P doesn't equal NP, what we're going to need to do is show that there is some problem that belongs to the class NP that does not belong to the class P. Notice that we did actually show that 3sat and longest path both belonged to this class NP. This means that if we were able to show that 3sat can't be solved in polynomial time, well, now we have an example of an NP problem that can't be solved in polynomial time. So P doesn't equal NP. If we could show that longest path didn't have any way to solve it in polynomial time, then we had now an NP problem that didn't belong to P, so P doesn't equal NP. So we've established now that regardless of how we answered the question of can we solve 3sat in polynomial time, we are able to conclude about the entire relationship between P and NP. If 3sat can be solved in polynomial time, P equals NP because it's NP hard. If 3sat can't be solved in polynomial time, then P doesn't equal NP because 3sat belong to NP. Similarly, if longest path can be solved in polynomial time, then P does equal NP because longest path was NP hard. And if longest path can't be solved in polynomial time, then P doesn't equal NP because longest path belong to NP. So once we answer the question of can 3sat be solved in polynomial time, we automatically know the answer for longest path as well, and for every NP problem. And for longest path, if we could answer this question of can it be solved in polynomial time, we can immediately answer the question for 3sat as well. So these problems that are in this group, where if you answer the question of can it be solved in polynomial time for one of them, you can make a conclusion about the other one. These are what we call the NP complete problems. This is the category of problems that are sort of together they stand, together they fall. Either all of them can be solved in polynomial time, or absolutely none of them can. So the definition of NP complete are all of the problems that belong to both NP as long as the class NP hard. So these have this together they stand, together they fall property, because if I took any NP complete problem and showed that it was solvable in polynomial time, then since they were all NP hard, they were the last missing piece in a reduction from any NP problem. Therefore, all of the NP problems, since they reduce to this NP hard problem, and that NP hard problem can be solved in polynomial time, all NP problems are going to be solvable in polynomial time as well. So since NP complete problems are also NP hard, the ability to solve any of them in polynomial time implies P equals NP. Since the NP complete problems also belong to the class NP, the ability to show that any one of them does not belong to the class P, that is, can't be solved in polynomial time, allows us to conclude that P does not equal NP, and allows us to conclude that none of the NP complete problems can be solved in polynomial time. So this NP complete class is very, very useful in being able to answer the entire question of whether the class P equals NP, because I can take any singular problem from this class, and the answer for whether or not that one problem can be solved in polynomial time allows me to draw conclusions about the entire relationship between the class P and NP. So having NP complete problems is incredibly useful because it helps us to understand the relationship between these classes P and NP. We take the question about these entire categories of problems and allow it to be answered by this question about just a singular problem. So now to show that a problem belongs to this class NP complete, since it's defined as the intersection of NP and NP hard, we just need to do two things. We just need to show it belongs to NP, which means that we need to show that there is some way we could take candidate solutions to that problem and verify that the answer should be 1 in polynomial time. And we need to show that it belongs to NP hard, which means that we just need to give a reduction from some known NP hard problem to NP, to this problem. So what we've done so far, we have shown that 3-sat belongs to NP hard because belongs to NP complete because we just took for granted that 3-sat belonged to the class NP hard. And we also know that 3-sat belongs to the class NP. So since it belongs to NP hard and the class NP because we gave a verifier, then we know that 3-sat belongs to NP complete. And then we showed that longest path belonged to NP complete because we reduced 3-sat to longest path. Therefore, we can conclude that longest path is NP hard. And we showed that we could verify longest paths in polynomial time, meaning it belongs to class NP, so it is NP complete as well.